Sergey, shall we start now? Okay. It's a great pleasure for us to introduce our today's special guests, Mats Bahrami from Academic Innovation, Wolfram Research, and Nikolay Murzin from Wolfram Institute. They will give a presentation on the introduction to Wolfram quantum framework. Please, Mats, please, Nick, the floor is yours.
Thank you for the invitation. Hello everyone. I hope everybody is doing well. Thanks for the organizers for this opportunity. So I'm gonna start with something generic, making sure it's mostly because I want to make sure all of us we are on the same page and you guys understand what we are talking about. Uh, I totally understand that we are living in a moment that procedural programming language are dominance everywhere. Okay, usually when you go to school, even without knowing what is procedural programming language, what is object-oriented programming languages, you are exposed to that. And sometimes the students they got this impression that, oh, okay, this is the only way that we do programming. Just a reminder, there are two main paradigms in programming languages. One of them are functional programming language, the other one is procedural. When we talk about Wolfram language, Wolfram Mathematica, keep that in mind, it's a functional programming language. So it's fundamentally different from most things that you guys have seen in your programming courses. So what you can do in Wolfram Mathematica, these are what you see a quick overview of main functionalities that you can do in Wolfram Mathematica. Basically, our mission at Wolfram Research is literally to make everything computational. And by everything, I mean literally everything. That's why see we cover various trends different topics from chemistry to geo all the way to calculus and algebra. Of course, today, our plan is to talk about quantum framework. So what is quantum framework? Quantum framework is a collection of functionalities that we build using building functionalities in Mathematica that basically helps you to do a seamless computation in a discrete space. Practically, I can safely claim that any computation, and by any, I mean literally, any quantum computation that you have seen in the literature, your textbook, in a finite dimensional space, it is doable to do it in Wolfram quantum framework. So it means you can run quantum gates, quantum algorithms and see the result, or you can basically set your Hamiltonian, evolve the system, and again, see how the system evolves and the corresponding quantum probabilities. So that's the story of our quantum framework. Very similar to everything that we have in Wolfram Mathematica. Remember, in our company, we spend a huge amount of our resources in our documentation. So I'm going to show you a few things about our documentation. So whenever you are working with Mathematica, keep that in mind. We have a very detailed documentation. I don't know, let's go through uh, gamma function. Okay, one of the spatial functions that we have. These documentations are very detailed, they start with the generic introduction, then you see the scope, numeric values, differentiation, etc., etc. And literally, our researcher, including myself, including Nick, whenever we do any coding in Mathematica, we always still code samples from our documentation. So do not forget, we spend so much resources on this documentation. They contain lots of interesting features. So always look into the documentation before, coding. And that goes, of course, with our quantum framework. So we have a very detailed documentation that covers literally everything. For example, let's go to, I don't know, quantum circuit operator. We are going to talk about that, okay? I just want to show you, the documentations that we have. So it starts with basic examples circuits, how to basically put the circuits. You can have, I don't know, state, rotation, noise, channels, etc. Then we go into more details, like, common gates, built-in, like, let's click on one of them. For example, look at here, Toffoli, Fourier transform, phase estimation, gray oracle. So you'll be surprised, like, how much detail, like, we have in our documentation. So make sure that you check our documentation. Last but not least, everything that we do, all the codes are open, accessible, like, you can, check it on GitHub. We would be more than happy to collaborate. And the easiest way to contact us is simply quantum@wolfram.com. So if any question, like, regarding, like, quantum, reach out to our team. We would be more than happy to collaborate and discuss with you guys. Now we are gonna switch the gears, like, Nick is gonna share his screen, and, like, we are gonna discuss about, like, quantum framework and what is it that we call as Wolfram quantum framework.
There it is.
Okay. It's visible. I think that, the font level is good. So as usual, remember, like, these are a collection of, functionalities that are not already in Mathematica. You just need, one line of code to add them into your, basically, like, Mathematica. So it's just, we call them, fancy name for those new collection of functions is Packlet. So you just need to run these 2 lines of code, and then, like, you're gonna get all the functionalities that are quantum related. And let's see, like, what are those that. So you see this long list of, like, functionalities that we have. And as I said, like, it covers more or less everything that is doable in a finite dimensional Hilbert space. Um, uh,
Excuse me, is it the full list of functions, or it's even larger? So,
Good
So there's
question.
some
So,
more.
no.
Maybe there's some hidden ones. So maybe those are not really functions, but maybe there's some hidden functions that are not in the this exported list. I don't
yeah.
know.
So basically, like, let's put it in this way. That goes also with, like, with the usual Mathematica, like, as some of you may have noticed from, like, Mathematica Stack Exchange or Wolfram community, like, when you ask some of your question, some power users, they will tell you, oh, by the way, like, there is this undocumented function, and you say, gosh, like, there is a strange function undocumented, and it does fancy things. The same here. Like, the functions that we expose with detailed documentation, etc., like, those are the core of, like, functionalities that we have. Then some domain specific functionalities, like, I don't know, like, you want to do a fancy tensor network contraction in a very particular way. Sometimes, like, those functions, maybe not all of them are exposed, but if a user is interested, like, they can ask us, and, like, and we would be more than happy to explain, like, what they do. So it's mostly like, we are following the same strategy, like, well, for Mathematica, like, also in Mathematica, some functions are undocumented, but majority of them are documented. And you see here, like, the documentation is exactly the same, like the rest of, like, documentation in Wolfram Mathematica. So after, like, by the way, if you don't install this Packlet, you don't see this documentation. So this documentation, as you see here on the top, you see, like, it tells you, like, the context dependencies Wolfram quantum framework. So in the old times, like, if you have some old time user of Mathematica, people, they usually refer to these things as packages. So, like, the headache with the packages was, like, the documentation, etc., and, like, dependency. But here is a modern version of that. Okay, so we can just call it library, or it's a collection of, functionalities to do quantum. Now let's see, like, we always have this, like, challenge. We always challenge ourselves, like, what is the best way of, like, sorry, representing, like, our functionalities. Uh, Nick, what do you think? Shall we go, like, from a high level and start with a circuit, or low level?
High level is, I think, it's better. So
Okay, so
circuits.
let's start with a circuit, which is, one of the beast, functionalities that we have. So the arguments that you can put inside, a quantum circuit operator is literally, like, any operation that you can imagine, like, in typical quantum computation. Of course, one big, feature is common gates. Now, like, let us explain, like, what we do here. So what we do here as argument, we are giving a list of gates, and those gates are simply like, the common names that we have for those gates. Whenever you are evaluating any of our functionalities, for example, like, Nick, evaluate that one more time. So what you see, first of all, is a summary box. Why we provide you a summary box, like, for many, different reasons, like, these objects, they contains lots of information. We rather to wrap it as a summary box. For example, like, this object is an object which is quantum circuit operator. Of course, all of them, they have traditional form. The traditional form for, like, quantum circuit operator is diagram. So you can, like, work at the level of, like, this diagram. What this animal does is you can see it as an object that does transformation for you. So fundamentally, like, in simple terms, like, the way that we design our quantum framework is there is a fundamental object that you save the data of your quantum system, let's call it quantum state. And then there are tons of other operations. Those operations, they do transformation. And everything can be done in the most generic way. Okay, like, what we are going to show you guys is simple case of, like, common quantum, but keep that in mind, like, there is no constraint for everything to be Hermitian, to be unitary, even, like, the density metrics, like, you don't need to impose the condition of, positive semi-definite. So everything can be very generic. Mostly because, like, we are going to explain there are some unconventional way of doing computation that are doable in Mathematica, and in order to support them, like, we have this generic construct. Let's look at the last line of code that Nick has evaluated. So what we are doing here is we are applying a circuit on basically nothing. What we do behind the scene is we feed the register state for whatever qubit that you basically set, in your circuit. And if you look at the diagram, like, it has 2 qubits. Now, let's see, like, from the very beginning, shall we shall we make it? Yeah, Nick read my mind. So in many of, like, those circuits, people, they do not explicitly specify, like, what was the initial state, but, like, that's like how we set the initial state. So basically we set both of those states as register state 0. It went through a transformation, and, like, we get the result. Just to make it a bit fancier, let's just start with a different initial state. So you don't need to start with the register state. You can start with the random pure state. That, pure generation, is done by a Haar measure. So it's uniform, like, in the space of, in the state space. And any other operation that we have in Mathematica, here Nick is creating, like, a composition. So what he's doing is, first he's creating a circuit, a state, and then it says the circuit that I created before applied on that circuit. And that's basically the result that you see here. Just to emphasize, like, look, you are, the environment that you see is Mathematica notebook. And one of the most important feature of Mathematica is that you can do symbolic computation. So let's do like this. What do you think, Nick? Like, let's have the initial state as symbolic, and then even for the rotation, for that phase, I suggest let's go with a symbolic phase.
Let's try this one first.
Yeah. So you see here, like, that circuit that we have, Hadamard, then C naught, and then, like, phase, it's applying on a generic state, and this is the result that you are gonna get. And then, like, you can do other things, like, you can define, like, a circuit whose phase is also symbolic, and then you apply it on a state that is symbolic, and this is the result that you would see. I want to emphasize, like, how important is this unique feature, because, Mathematica, at least for quantum, is maybe the only platform that you can do symbolic quantum computation. And the history of quantum computing, it has evolved such that most tools that were available from the very beginning, none of them supported symbolic quantum computation. Because of that, like, the common narrative in quantum computing community, it's not based on symbolic quantum computing. For example, if you go through the literature, etc., like, you don't see like, okay, let's do algorithm design following symbolic quantum computation. So this is the thing that I want to emphasize. Like, this is really uncharted territory. Like, when you think about like, quantum computing, how symbolic quantum computing may look like. So like, just a very interesting, like, topic for future research. Now, for that circuit, like, what else, like, we can do on the, and by the way, if any question, please stop
Yeah,
us and ask, please,
I have a question. May I
please.
ask? So you initialize your circuit, and there is a width of 2 qubits. So it was automatically determined from the CNOT operator, right? Or you
Yeah, the
determined
maximal
it?
RT. Well, it's just
Okay.
determined by, well,
And
what
what
you
if you introduce two, for example, two CNOT gates? How you put determine which 2 qubits
Okay,
or
so
which pairs?
good question. So like, I think, let us start like, with the, like, where we, so uh, in our framework, like, we have a feature, like, we call it like, order. So basically you see like, the second argument after each of those gates is where we are telling where that operation is acting. So for example, the second CNOT, you see like, we are saying the control is the first one, the target is the third one. And you can do like, whatever way you like. Like, it doesn't need to be like that. Like, you can design it like, whatever way that you want to do that. Now Nick is making like, even fancier, like, adding swap, or like, you can add permutation. And again, like, when I told you any computation, like, I mean that. For example, let's see, a fancy quantum operation, like, now, uh, 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 let's see, let's challenge ourselves and let's do, let's see, shall we do like, switch, quantum switch? Now I have to remember, like, quantum switch is basically a fancy way of like, applying uh, superposition of, like, as Nick is basically playing around, like, with the permute.
I know what's going on. Yeah, but
Okay. So this is the case of like, permuting. Like, so basically, 1, 2, 3, like, you see like, the one is going to the third one, number two is going to like, number two is going to the third, like, now I have to remember, like, how we should read, like, that cycle. Yes,
yeah,
and then number three is going, number two to the third one, number three to the first one, and number one to the second one. By the way, I know it's very easy to read it of the circuit. Try to read it of the permutation that you define. Like, for example, 1, 2, 3 goes to 3, 1, 2. Like, that was basically what I was trying to do. Uh, let's see. Uh, for example, like, Nick, let's wrap one of the as the final state. Let's add into that circuit uh conjugate transpose of a state. I don't know, like, do you want to wrap, I don't know, wire number 2 and 4 by Bell state?
I mean, you want do it like this. Well, it's Bell state. Oh, it's a circuit. It's a circuit for the Bell state. No, it's a Bell
Okay.
state.
And then as a final state, like, for at the very end, number 3 and 4, like, add, like, a dagger of the Bell state there too. Just to show you guys, like, what's the, and look at, like, the transformation. Okay, now add it on, I don't know, whatever wire we want. So you see here, like, this is basically like, and by the way, very similar to Wolfram Mathematica. One of our headache when designing quantum framework was like, make sure that it is readable. For example, let's just look at the code. We are saying, like, there is a quantum state. That quantum state is Bell state. As you see, that Bell state, it doesn't have any order. There is no number in front of that. So automatically we start from the first wire. And because the Bell state is a 2-qubit quantum state, we say, okay, so it's going to be on number 1 and number 2. Okay. If you specify an order, I don't know, like, let's go even in the initial Bell state. the first one, add it as 1 and 4, for example. Now, like, it's a bit fancier. I hope, like, you can see, like, it's coming out of the first one and the fourth one. And then, like, Hadamard, CNOT, etc. Now, let's make it fancy. I don't know. Like, let's add a bit flip on, which is a quantum channel, like, on the fourth wire. So this is a bit flip of, like,
Oh, because hold on, let's just get rid of this.
Yeah. So now we have, like, a bit flip. What else? Like, what other unconventional, like, oh, let's add measurements. We forgot to mention, like, let's also add, like, measurements on some of our wires. And let's do like this. So Nick is adding measurement on the first one and the second one. Now, just like, some cosmetic touches. So you see here, like, we are starting from a Bell state for qubit number 1 and number 4. Then qubit 2 and 3, automatically they are register state 0. Then bunch of operation. Those operations, they can be anything. Then we say, like, now let's project qubit number 3 and number 4 into a Bell state. And then a bit flip, which is a quantum channel, is acting on the second qubit. And then we are going to measure qubit number 1, qubit number 2. Of course, it's like, a fancy computation. I don't know, shall we dare, like, Nick, looking at the probabilities? I think it's going to take some time because, everything is,
Yeah, well, let's just make a numeric phase.
oh
Just
yeah, let's look at.
Excuse me,
And
what does it mean, bit flip 1/2 in the brackets?
good point. So it means the quantum channel, like, so basically, what was the idea? So 1 minus P, P is the probability of noise happening. Nothing happens with the probability of P, a bit flip happens. Basically, like, not gate happens. So basically, like, that's how you can include noise in a deterministic way. So keep that in mind, like, this is a deterministic way of, like, including noise. Of course, like, one can add noise, like, in a stochastic, non-deterministic way. That's a different story. We can also talk about that, like, how you can model it in mathematical. That's basically, that bit flip, that quantum channel. Think about it, like, you have your cross operators, and the cross operators are sandwiched between, like, your quantum states. Like, that's the idea of, like, quantum channels. That's the way that we model quantum noise in a typical circuit. Now let's see, like, that circuit, what else we can do on the top of that circuit, like, let's do, like, a conditional, like, measurement, the way that we do in measurement-based quantum computing. For example, before the bit flip, let's add a conditional measurement, like, we would say, like, I don't know which, let's measure again, qubit number, I don't know which one. Shall we measure qubit number 2? Let's, qubit number 2. Let's okay. So and that's basically, like, the, like, look at, like, the operation that we are doing here. So it's a typical operation that you can do, which is very common in measurement-based quantum computing. I know, like, we are combining many things together, but, like, just to show, like, we are saying that, look, let's read qubit number 1 and then condition on the result that we get there. Let's act, like, on qubit number 2. And of course, like, you can have any conditional operation as you like. Somebody may ask, oh gosh, was there any question?
That was just
Oh, okay.
occasional noise.
Someone may ask, oh, okay, so how, like, you guys went through lots of headache, like, to include, like, in all of these spatial, like, operations, like, in mathematical. So each one has its own customized way of doing things, etc., etc. I should say, because we have very powerful algebraic, computation in mathematical, including all of these operations, it was relatively straightforward. I'm not saying, like, it was easy, but because Mathematica understands any form of like, symbolic computation. So you have the freedom of like, adding any fancy, and by any fancy, I mean like really you can do like, lots of, fancy operation on the top of like, your measurement results. For example, let's say that like, we are pure quantum, the scientists. We take quantum very seriously, meaning like, uh, whenever we do any measurement, the measurement is simply like, we are entangling like, our quantum system with a larger system that lives like, in a higher dimension. Okay, so Nick, I wanted to, let's show like, the higher dimension, and then we can talk about tensor network too. So those measurements, this time for the diagram, let's show them like, the extra qubits. Okay. Um, everything that we have shown you so far, like, everything was happening in, the dimension 2, right? Like all of those, fundamental quantum system, they were two-dimensional qubits. Maybe I had to reminded you from the very beginning. In Wolfram quantum framework, there is no need to basically come say, oh, everything should be like, in dimension 2. The dimension of your system can be anything. And you have like, the possibility of like, generalizing everything that you into any dimension. For example, look at, the initial state. Nick is creating a random pure state following like, hard measure for dimension 3. Then he measures a generalized Pauli Y in dimension 3. He gets like, that, probability distribution for the result of like, measurement. So that's basically a quantum computation that you do in dimension 3. Of course, you can like, just to make sure that like, it's clear. Let's start with an initial state. Nick, make your initial state a state of, I don't know, 2 and 3. Let's make sure that, we are not just talking about like, the dimension can be anything. So look at this case. So we are talking about the quantum system where the first quantum system is a two-dimensional quantum system. The second one lives in, dimension 3. And then like, and of course, like, this is the, in case show the wire dimensions, that's how you can also visualize that. So you see here, like, here we are saying that, we start with an initial state. The second wire is two-dimensional. The third wire is three-dimensional. And then you can do any operations that you want. Of course, for future operations, you have to be careful because your basis dimension is not 2. For example, like, let's add a C naught without specifying the basis. Okay, just say it's C naught. Okay, so you see here, like, there is kind of like, an issue because if you do not specify the dimension, automatically behind the scene, we are going to assume everything is qubit. Okay, so you see here, like, the C naught that is acting, it has the dimension like, 2 and 2. And of course, like, if you want to evaluate, like, what's going to happen, like, next, it's going to look very strange. So the way that you have to operate it is simply saying, look, it's a conditional operation, but the target has the dimension 3. So what we are saying here is like, we are saying that like, that that knot, it is happening in dimension 3. And that's how basically you can define this is a C naught with a target, now I'm forgetting, like, how do we call it? Q treat? Like, how
Yes.
do we call it? Q
Q3.
treat? Q treat. So the second quantum system is a Q treat. Okay. And that's how basically you can define, your operation. Um, so we mentioned, like, the dimension, you have absolute freedom on dimension. Uh, uh, in the latest mathematical version, there is a very unique functionalities. It is called symbolic array. So basically, like, in those functionalities, the dimension of your matrix or your tensor, it can be, symbolic. You don't need to specify, like, what is the dimension. You can just say, okay, it's like, arbitrary. For example, like, here, like, what we see is that rank 3 tensor. Okay. We haven't incorporated this very fancy new feature into our framework, but it's going to be like, future work. So basically, think about it like this. You are working with some quantum system, and what is the dimension of quantum system? N or A, B, and C. What is A and B and C? They can be anything. Let's run like, our operation. Let's do any fancy things that we want to do and just, limit everything into those symbols. Okay. So that's the idea of like, again, like, symbolic computation. Now let's go one step further, make things like, a bit fancier, like, how we do the computation behind the scenes. So Nick, show them the tensor network. So what we do behind the scene is basically like, tensor network contraction. You can see like, the tensor network that like, that we create out of that circuit. So basically like, now going from, let's show the circuit diagram at the same time together with the tensor network. Okay, so that particular like, circuit diagram, it has this corresponding like, tensor network. And you can do any any fancy operation on the top of your tensor network. So when you are evaluating your quantum circuit, what we do is we do all the tensor contraction that should happen on the top of this tensor network. But you have the freedom, like, some of those functionalities that are not completely documented, you have the freedom of like, doing any fancy tensor contraction. For example, you can add like, edges to your tensor. You can like, remove one of them. You can just contract a very specific location. So what else? What other interesting feature that we have for our tensor network, Nick?
Well, it's mostly like a computational helper. It doesn't have to be user exposed, but just it's still interesting how the underlying mechanism works for quantum circuits. It's like any operation that you see, including measurement channels, mixed operators, which is like density matrices. You can use not just pure states, only you can also use mixed states. And those fundamentally just compile to a tensor network, which is just a graph where your vertices are tensors, and you just only specify which indices of those tensors has to be contracted. And you just compute the resulting tensor of all of those contractions in the tensor network, and that's your result. Right? You don't necessarily have to work with it directly, but you can, like, there's some functionality, but it's not very documented anyway. You can add tensors to it. I don't even remember how it works, so because I don't use it often. So, but yeah, there's
This would be interesting for those people, like, let's say that, like, you have a very fancy, like, network, tensor network, and you just want to get your tensor network. And then when it comes to basically, like, doing the tensor contraction, you would say, okay, I want to do it in a fancy way, using GPU, etc., other things. So, like, those are like, spatial, like, use cases that people, they can, they can use. Uh, let's see what other interesting feature, like, any question so far, like, I'm planning to change the gear going from fully
something.
Good question, like, now there's a question like, Nick, are there any optimization used for contraction of tensor networks?
Not really. It's just because we don't assume that this framework is used for highly loaded problems, like up to dimensions 30 and 40, like the actual edge of the quantum computation that can be done at the classic computer. We mostly emphasize the like some small circuits that can be explained, right, and visualized, so that it's mostly for educational purposes. To implement those polarizations, there's some works in that regard, but it has to be supported because we work in the Wolfram language ecosystem. It has to be, if you want this kind of polarization, it's also the question whether this kind of things work for everything else. Like, can we do this optimization on neural networks? Like, if the
Yes.
neural network framework is like another completely different thing in the Wolfram language that also has tensors and some computational graphs in there, right? And it's like the question whether we have to use their framework and their work for this kind of optimization. So it's not like to implement it twice, anything like that, or use some better libraries that support both of the operations.
The other reason is that, like, many of those, optimization for tensor network contraction, they are hardware dependent. Okay. So like, basically like, what is the optimized path of doing tensor contraction? It depends what type of hardware you're using, basically. Like, are you running that on GPU? And if that GPU is NVIDIA, is it AMD, is it like, Intel, etc. And depending on them, like, you may end up with a different, like, optimized path for your tensor contraction. For those cases, if somebody wants to do those very fancy things, in Wolfram Mathematica, you can seamlessly work with any other programming languages. We always recommend, like, for example, CUDA-Q and, like, all those libraries. Like, you can easily start from here, do all those your prototyping and everything that you want to do. And then from the point that you want to do, like, fancy, very heavy numerics, just switch to, like, those domain specific functionalities that are best designed, for example, for that very specific purpose. I hope we answered the question. Let's see. Uh, Now talking about, like, integration with the other platforms, like, let's see, like, do you want, like, to, show, like, the integration, Nick, with the, for example, like, elephant in the room, Qiskit. Many people, like, they work with Qiskit, like, shall we show, like, how they can go from our framework into Qiskit, come back? So basically what you can do is in Wolfram Mathematica, you can directly go to any other programming languages, like, so basically, like, in the same environment, you can run, like, whatever, like, you want in Python, in R, in, like, practically any common programming languages. And what you see here, we just went from let's look at the diagram in Wolfram language 2, just, show the diagram just for the sake of. So you see here, like, we went from a quantum circuit in Wolfram quantum framework to a circuit in Qiskit. What is it? Remember, like, Wolfram Mathematica understands the statistics, meaning whenever we are calculating the result of any quantum operation, which is a probabilistic, like, description of whatever is that system, we do not do frequency counting. We don't do that. Like, that's the thing that I want, like, everyone to pay attention. Like, it's just, for example, we don't run, like, a circuit, like, 1024 times to get, like, the frequency of, like, different events and say, okay, like, because it's large enough, it approaches, like, the prediction of quantum theory. That's not what we do. We do, like, those computation exactly because Mathematica understands, like, statistics and probability. So that's one fundamental feature, the difference between us and other quantum platforms. But anyhow, like, this is, the Qiskit. Now I have to remember, like, let's look at the chasm code. Like, I'm sure, like, there are some users here, like, who know chasm. So this is chasm tree code. Let's look at from the Qiskit. Let's look at the chasm. Do we have chasm? Chasm 2, was it from the Qiskit? Or now I have to remember, like, I don't use it myself that much.
Oh, me neither.
Just chasm. I think, like, you have to remove the 2, or
No, it also works.
oh, it's also work with 2. For, like,
I think it has both.
chasm 3, the way that, yes. And then, like, whatever you have in Qiskit, like, if you want to do transpiling, if you want to do, like, whatever, like, it's completely doable here. Um, by the way, any of these circuits that you see here, you can send it to any hardware that is publicly accessible. So, like, that's also completely doable. It's just like, you create your circuit, and that circuit you just feed it to, like, as a job, like, by connecting to their API, you just, send it to their corresponding, like, hardware, whatever is that hardware. And here, like, for example, we started, like, Nick started with the multiplexer that, yeah, good. So you see here, like, that's a multiplexer, one of those, like, computationally heavy the circuits. And then, like, you can go to Qiskit, you can, like, do all the transpiling, whatever, options that we have in Qiskit, you can incorporate it here. Now this one should take longer because behind the scene, yeah, you see here, like, the depths of the circuit is relatively large. Now, a quick side note, like, although like quantum computing is very popular and many people are talking about like quantum computing, but the initiative that we have at Wolfram Research with regard to quantum is not only about quantum computing. So basically for us, the big umbrella is quantum itself. And quantum can include many different things. We can talk about like uh, 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 open quantum systems, like how you would model open quantum systems and how you would incorporate like noise and how you basically like different like master equations, how you would simulate them, etc., etc. So we have like full support for them. Maybe after like, so Nick, what he's showing you guys here is just he's going back and forth between Qiskit and Wolfram quantum framework. Okay, so like just to show you like both ways are possible. um uh, the other thing, like quantum sensing, quantum communication, like all those like any field of research, quantum chaos, like quantum thermodynamic. I myself, I'm coming from like open quantum system background, so like I do lots of like open quantum system. So don't think like when you talk about like quantum is only quantum computing. There are very interesting like quantum phenomena out there that are very important for application, and many of them like the technology is available today. Okay, so that's the thing that I want to emphasize, like especially for those students, like keep that in mind, that like many things that you learn for quantum computing, they are the promise of the future. Okay, like I remember like 15 years ago when I was PhD students, like they were telling us next 5 years, next 5 years, and like we are still waiting for that next 5 years. Like I know it's a very complicated like engineering problem. Many big companies, big governments, they're allocating resources like to develop and reach the point that they can claim that yeah, they have a universal like quantum computer. Having said that, there are many other interesting like quantum phenomena with direct application. Now, the other branch of like our research cares about quantum foundation. What are basically fundamental questions like regarding quantum? For example, like um, I don't know. Let's say that like in quantum optic, like you have the second quantization formalism, and you want to basically model all those fancy like the features that we have in quantum optic, and then you want to, I don't know, like a non-linear like Hamiltonian, and then noise, and then loss of photons, etc. So all of them are possible. Like at least let's show them some of the functionalities that we have there. For example, like an annihilation operator, cat state, coherent state, like commutation, displacement operator, fuck state, like Husimi representation. I don't know. Let's create like a random quantum state, and let's look at like now some of them. I think like they have good documentation. Or I don't know, Nick, do you want to show one example from the documentation? Maybe if you click on a Wigner presentation, I'm sure. Oh, did it crash your kernel?
Oh, sorry.
And sadly, like these things happens. Like it's
Nope, not clicking around in new versions.
what version, by the way, like what version of Mathematica you are using right now?
No, it's 14.2.
Okay. Nick is
Maybe
always using like the prototypes. Like I'm not that much fancy. I always like use the versions that are officially released. So Nick is always like one step ahead. So this is not a released version. So some of like bugs, etc. Like they are still there. So it's not completely clean version. So let's try one more time. Like second quantization, just as the last example for today. Let's see. And let's go to, I don't know,
can't find
second
it.
quantization functions.
No. Okay.
Yeah, if you scroll down for, I guess at the end somewhere, so that's those current state. Yeah, you see here like these are like Wigner representations of like uh some quantum states, and like I just wanted to show you guys that when we talk about like our framework, it's not just about quantum computing. Like it supports like many other things. um so how much more time do we have? Like shall we open it to Q&A, or like more or interactive discussions, or For example, like what you see here is a Wigner representation of a Fock state zero, that zero state that you guys have learned in your quantum optic courses, if anybody has taken quantum optic course. And then you can do all those fancy, I don't know, anybody here remember revivals, that you guys learn in your quantum optic? Nick, if you scroll down, yeah, you pass that, when it goes up, and yeah, the one above that. Yeah, that's a typical example of revivals, etc. But anyhow, uh, remember, the story of our efforts on quantum is not just about quantum computing, although quantum computing is taking a big chunk of our efforts.
So you mentioned open quantum systems. Could you show the documentation on open?
Oh yes, let's go another there are some functionalities in uh, uh, the same with mathematical, some of our functionalities, they are big functionalities, quantum evolve is one of them. So what you can do is you can these are some examples that you see here. For example, this is a symbolic way of calculating T1 and T2 relaxation for one single qubit. What you have to do is set your Hamiltonian. So here, our Hamiltonian, as you see, is, or maybe Nick, instead of 100%, make it 150, so they can see that. Yes. So look at here, quantum evolve. We are saying that the Hamiltonian is basically JZ. Then Lindblad operators, so basically that's our Hamiltonian. Then we are saying what are the Lindblad operators? We define them on the top. So it's basically plus and minus and GZ itself, and the corresponding rates are T1 and T2, the conventional one in the textbook. And then we just tell Mathematica that, look, evolves it with these things. So Mathematica understands that the Hamiltonian is the first term, the second term is your Lindblad operator, and then as quantum state, I just gave it a symbolic quantum state. I just say let's go with an array of rho, and by the way, that rho can be either pure or it can be a mix. So you see it's rho 1 1, rho 2 2, rho 1 2, it's generic. I'm not specifying anything. And that's basically the evolution of that system. Of course, Nick, go to generalization extension. There are some fancy examples. For example, Lindblad master equation for density metrics in Schrödinger picture, Heisenberg picture. All those fancy evolutions that you have, you can easily simulate that. And by the way, it's, we didn't emphasize that much, since, the usual story of quantum, we can have a Schrödinger picture, you can have Heisenberg picture. For example, you can evolve your state, or you can evolve your, operators, or you work in the interaction picture. All of them are possible here. But anyhow, this is
But
that.
may I interrupt you by the question? I see on the block sphere several bases, three pairs of bases. How is transition between the bases done?
So fundamentally, we said we always go with, if you don't specify it explicitly, we go with computational basis, basically Pauli Z. Okay, the eigenstate of Pauli Z. That's how we would define that. Unless you say it explicitly, what else is going to be the basis? We are going to treat it as computational basis. How you can change that? The second argument in the quantum state is always tell you what is the basis. For example, look at the example that Nick is showing. Nick created a zero state in computational basis. Then he says, transform it into Pauli X basis. So that's a transformation to Pauli X. Transform it to Pauli Y basis. So that's a transformation to Pauli Y. And of course, you can, create any, I don't know, Nick, go with the symbolic one that instead of zero, make it fancier, like A and B. And then that's a transformation for Pauli X, Pauli Y. So, and by the way, because you're just changing the basis, fundamentally, these states are the same. That's what Nick is showing you in the last line of that code. So it doesn't matter, what basis you are working. How the transformation is, if you're asking how the transformation is done, it's the usual, basis transformation with a unitary that takes from one basis to another basis. Like, that's how you can understand that. And then the story, like, we didn't discuss about that. The story of basis, it can be anything. Like, so here we are just talking about, like, the approach that, you think about, like, for example, your block sphere. You can have literally anything. You can think about, like, I don't know, like, phase space, where, like, your basis is gonna be, like, not only, like, up and down. It could be, like, for example, like, Wigner. Okay, Nick is showing you, like, one of the examples. So this is, Wigner in discrete space. Remember, like, many of you, Wigner in continuous space. This is Wigner in discrete space. This is Wouter in discrete space. We also have Feynman, Nick, right? Like, yes, we also have, like,
It's the same as others.
okay, it's
For 2D.
some of them are less popular. Like, I guess, nobody has said, oh, Feynman, was there a quantum basis in discrete space? Like, with the name Feynman. Oh, yes, like, Feynman in his famous paper on negative probability, he introduced, like, this basis. And then, just for the sake of presentation, some of these bases are completely unconventional. So they give you the phase space representation, meaning this is the story of quasi-probability, etc., etc. So we also support all of those transformations. For example, like, look at here. Starting from that symbolic state, like, A and B, this is the presentation of that state in Feynman basis. And Nick, like, let's give it numeric just to show people, like, the quasi nature of, like, some of these bases. For example, like, you see here, one of them is negative. So, like, you cannot interpret all of them as probability. Now that's the story of quasi-probability. And, like, we are actively working, like, this is one of those field of research that some people, they call it, like, the geometry of, like, quantum states. Like, some people, they call it phase space representation. So we are actively working on that. And, if any interest by, like, any researcher here, like, please let us know. We would be more than happy to collaborate. And I'm gonna put, one link, our latest preprint on archive, which is about, like, this topic. That's basically, like, a fancy way of, like, playing around with, this geometric approach to understand quantum state.
Mats,
And by the way,
sorry to interrupt you. You've said about different bases. In which one the master equation, the Lindblad equation, is solved?
if you don't specify that, it's gonna be computational basis. So we do it, like, in computational basis. But very good question, because the example that we showed you, it was not in computational basis. I wonder if you noticed when Nick showed you the traditional form, it was, like, JZ up and down. Okay, but anyhow, like, we do all of the computations in computational basis unless you specify a different basis. So we do it in that basis. And if you want to know behind the scene what is happening, we are just using, like, ND solve or D solve that we have in mathematical. Like, that's basically like solving this fancy differential equation. So basically what you can do is this. Specify your quantum state in any basis that you like. Specify your Hamiltonian in any basis that you like. Specify your Lindblad operator in any basis that you want. Behind the scene, we would put all of them in one quantum basis, and we are going to solve, like, the solution for you. And you don't need to be worried about quantum, your final state, because the result that we are going to give you, it is also in a given specific basis. If you want to see the basis, just ask what is the base. For example, Nick, show a quantum state in a generic base. I don't know, any basis, just as an example. For example, let's say that you don't know what is the basis of that. You can ask explicitly, what is the basis of that system? And just show the association. So yes, okay, you read my mind immediately. So this is the basis in which that quantum state rho is defined, which is what people usually call as computational basis.
But if either Lindblad or Bloch equation is solved not in the eigenstate basis, but in any other one like this physical basis, the relaxation may happen from lower level to upper one. Do you see what I mean? I mean that in 0, 1, which one is lower?
I
Which
know,
one
keep that in mind. Like when we are solving that, we bring everything into the same basis.
I
You know,
see.
like,
So the relaxation terms are also transferred into
yes.
Right.
Basically, like, the main motivation behind this design for us is this. Any quantum object, let me call it quantum object, okay? Your Hamiltonian, your Limblad operator, your quantum state. Define it in any basis that you like. The basis can be literally anything. When we want to solve them, we are going to bring all of them into the same basis. Basically, we are going to make sure that, hey, everything is in the same basis. Otherwise, we are going to end up with the problem exactly as you said. Like, in one case, like, it could be like, relaxation. In the other basis, it means, for example, excitation. Yes. So we would bring everything into the same basis before doing any computation. Like look at this case. Like, Nick is showing you one example. So in the first case on the top one, the state is in computational basis. In the second case, Nick is feeding the basis in poly X. But when we solve that, we return the same state for you. Like, we would take care of, like, basis transformation.
I may also
Please.
want to make sure. I think Sergei Nikolaevich is saying that when we try to write down the Bloch equation or Lindblad equation, we want to make sure that the relaxations are written in eigenbasis of the Hamiltonian. And neither of these representations will change in time, so the relaxations may not be introduced correctly for such simple treatment.
No, I understand that. What you guys are saying is that, like, one has to be careful about, like, the basis. What I'm saying is that, yes, behind the scene, like, we transform everything into the same basis. Keep that in mind. When you're defining your Limblad operator, if you make a mistake at that level, we are not going to correct you in the future. So we are not going to basically, like, say, oh, by the way, remember, like, you define your Limblad operator in the wrong way. That's not what we do. What we do is whatever you give us as a Hamiltonian, as a state, and as a Limblad operator, we transform all of them into the same basis. And when we do the calculation, everything is done in the same basis. Like, look at, like, the examples that Nick is showing you. Like, he's transforming, for example, Hamiltonian into a fancy basis. He's transforming a state into a, like, a different basis. But all of these results are still the same at the very end. But yes, if you don't care, if you are not careful with the basis, instead of relaxation, you may introduce excitation. That's why, like,
okay, sorry.
Please go ahead.
Could you please show how to calculate a scalar product of two vectors, let's say arbitrary coherent states?
For example, like, I don't know, like, Nick, do you want to go with the coherent state as in quantum optic?
Yes.
Okay, so, like, for example, like, this is, one of them. Then specify, like, maybe a different one, like, and, we can simplify that. The story of second quantization, the way that we do it right now, we do a trick that, some people, like, in the literature, they call it, like, truncation of your space. Okay. So basically, we are going to say that, what is the default size here? 16. For example, we are going to say, look, for this very specific state or this very specific, like, Hamiltonian, if you include up to 16, that should be enough for all practical purposes. You may say that, hold on a second, like, the dimension, that truncation that you're doing is not large enough for my purpose. Like, I have lots of particle creation, and if I truncate only up to 16, that's no good. I have to go like, beyond 16. So what you can do is, set focus space, like, what was the function? Set space size. You can set it at 20. So now, like, the truncation will be done, like, up to 20. That's how basically, like, it is done. So the trick that we are doing right now is truncating of your focus space. Meaning there will be always some numerical error. Like, that numerical error, like, one has to be sure, like, it is negligible for all practical purposes.
Okay, I see. Thank you. Also, a second question. I saw annihilation operator, but I didn't saw creation operator. Why is
Oh,
that?
it's the dagger of that one. So just, yeah. The creation operator, you'll be surprised, like, everything that we have in mathematics, it's literally like, the same
okay.
thing, that it's just
Okay,
dagger of
thank you.
that one. So we could, that one thing that you guys should know, creating a function is usually very costly in terms of, it's going to take lots of resources from you. It's going to, like, it's really expensive, process to have a new function. So even some of the functionalities that you see here, we call them experimental functions, meaning as our users are working on that, and as we, like, develop more, we would love to reduce them into some master functions, because the less functions, the better. The more functions, like, it's usually, like, more complicated. So that's the main reason that we don't have creation, because creation operator is just a dagger of annihilation operator. Or you can, like, define, like, if you look at our documentation, like, our developer, he always does it like this. He define, like, annihilation, and then, like, with just a, like, oh yeah, this is a number operator. Nick showed, like, the traditional form of number operator, like, that those of you who know up to, you see here, like, that's up to, you see, like, here we set the focus space size as 20. So up to 20, it looks like that. Our future work, like, is to incorporate those, like, symbolic arrays, and have, like, a full description of second quantization in a real focus space. And of course, like, all of these things they're available on GitHub, and and we are open to any feedback, any contribution. Like, just let us know. What else?
Or we can discuss measurement in more detail. I don't know.
Do we have more time? I don't know how much more time we have. Like, there are a lot we can discuss. I'll just pause, because I'm not sure how much more time we have.
Yeah, we can slowly go transform to questions and answers, since we had already some questions.
Okay, so let's do Q&A. Tell us.
Yeah, you
Give us a
mentioned
hard time.
you mentioned about noise, so I
Yes.
wonder whether you have some noise models implemented.
The idea of noise, there are two ways that you can go after noise. One of them, like, the conventional textbook example is quantum channel. Okay, so all the famous channel, maybe that visualization is very helpful. Yes, if you, yes, yeah, you see here, like, all the famous, like, noise channels that we have, in quantum, bit flip, phase flip, like, bit phase flip, like, depolarization, amplitude, damping, phase damping, and then some generalization, reset error. So all of them are, like, the conventional ones are there. Nick, if you scroll up, the function quantum channel, literally what it takes is a collection of cross operators, meaning you can have any noise that you want. So just specify what are your cross operators. You remember, like, the example that I was showing you guys for T1 and T2 for that, like, spin system. So I just specify, like, the cross operators like that. So these are, like, the built-in, channels, and that's how you can model them. So this is the story of noise in a very deterministic way. Now, if you guys are asking, like, what about a dynamical equation that is stochastic, and then you want to make it nonlinear, it's gonna be like, you know, a completely different story. And let's see, do I have a, you know, that undocumented functions like, you know, that we have now. Let me think if I can find it quickly. Nick, you know which one I'm talking about? The state diffusion examples.
Not really.
Let me see.
You have a,
I
is it
might
really
have.
functions that we have or just the notebook?
No, the notebook, because like, you know, I'm gonna say like, you know, why we haven't added them into our, where did I put them? Okay. I have, if I may share my screen, Nick, very quickly, I can show one example. So these are the case of basically noise as, you know, literally like, you know, a random process, and like, you know, how you would, you know, simulate that, like, you know, for, you know, many, all the textbook examples, like, you know, you can get like, you know, your limb blood, and then you can like, you know, simulate like, you know, your system, you know, using noise, the usual, like, you know, spontaneous, like, you know, diffusion, and then like, you know, the stochastic evolution, like, you know, do the, you know, noise averaging, all of those examples, like, you know, homodyne, like, you know, measurement, heterodyne measurement. So all of them are doable. Why we haven't included them as built-in functionalities? It's mostly because any of these noises, there are infinite different way of specifying is a statistical properties. So these textbook examples are just simple examples. I'm sure any researchers who is working like, you know, with these noises, they would say, oh, I don't want, for example, to have this noise. I don't want my noise to be white. I want to make it like, you know, non-white noise. I want to change the coloration function. I want to do this. I want to do that. That freedom is literally like, you know, the features that as of now, we do not have a good master function that can incorporate all of them together. Okay, so basically like, you know, why we don't have a building function that does that explicitly, because we design wise, we're still not convinced if we should leave it to our users to basically simulate it the way that I'm doing here. I'm just saying, you know, look, you know, this is a Hamiltonian, these are the limb laws, and the noise is white, and like, you know, go solve it with, you know, this dynamical equation. Okay, so that's literally like, you know, this is a Wiener process. That's how, like, you know, I'm specifying that. I'm not convinced if we will end up with a situation that can be universal for every researcher, every user. So that's why this is one of those ongoing, you know, projects that we have in our team. So shall we like, you know, introduce like, you know, one functionalities that covers everything, or we should do something different? You know, when it comes to the noise and all these like, you know, diffusion, etc., then like, you know, scientists, they have two different like, you know, tastes. Somebody, they love Ito process. The other people, they like, you know, Stratonovich process. Which one we should like, you know, incorporate? Shall we support both of them? So it's it's kind of like, you know, lots of freedom, and having one or a few functions that covers all of them. At least we don't have a unique solution right now. If you guys want, like, you know, I can share like, you know, those notebooks for noise, but like, you know, that's basically how we go after noise in quantum systems. I hope I answered your question.
Yeah, thank you very much. Yeah, fair enough. So please, I invite everyone to ask questions.
Please, any question, don't be shy, like, you know, it's
Perhaps from students as well. Yeah, Mykola Bondarenko, please go ahead.
I was wondering when you mentioned that Mathematica is good in doing the dimensionality arbitrary, you mean symbolic operation with dimensionality. So can you, after all, do it a non-integer, you know, just to investigate phase transition like that?
Well, not in our framework, but in Wolfram language in general, at least some functionality already present that does, for example, like fractional differentiation and differential equations. So I personally don't know anything about those, but maybe just a little bit. But some functionality is there, so, but not the symbolic ones.
Okay, thank
That's
you.
what I remember.
The symbolic ones are like, all of them are integer. So, but
Yeah,
as Nick said, like,
assumed to be integer. You can set
yes.
them symbolic and maybe ask some simple questions. Maybe when you multiply symbolic matrices with symbolic dimensions, what's the resulting dimension? You get this kind of inferences you can do.
Yeah,
I'm not
okay.
sure whether you can actually assume that they're not integer. Maybe you can.
Thanks.
So you mentioned also that the neural networks framework. So do you have experience in combining these to, or just you have some ideas but not so much experience?
We even tried, because we also tried making some explicit examples for doing quantum machine learning when it's like people make some circuit and then try to optimize some parameters of that based on some metric or something like that. And the correct way of doing it and actually combine it with the neural network framework, right? But it's a little bit more problematic because tensors work in a completely different way in both of the frameworks. It's like because there's usually some complicated backend in the neural framework that is assumed, right? Maybe it's running some complicated backend that you try to ask for a gradient and everything like that. But when you do quantum circuits, there's some complicated way of constructing tensors. There is no yet like a common ground, but we're trying to merge those things together in the Wolfram research. But yes, it's like two problems. You have to have a nice computational graph corresponding to a quantum circuits that's a parametric, like having some parameters that you can then track your gradient through and then do your conventional back propagation and compute the gradient and loss function and adjust them. And you do this quantum circuit, classical tensor neural network things together. Those kind of examples.
Thank you. Yeah.
Let me also mention one thing, like, because, I know majority of people are here from academia. I'm just going to show one specific example, like, a recent interaction that we had with some of our researchers. This is a cover of, like, physical chemistry journal, and I guess, like, you guys can identify, like, this is like, the things that we were showing you guys. So we help, like, these researchers, like, and their work has been published on physical chemistry layer, and it went to the cover. And by the way, we were not involved at all as author, co-author, or anything like that. So when I say, like, we would be more than happy to help and collaborate, don't think like, oh, these guys, like, should be, like, co-authors or, like, in order to help us. No, like, we love our technology and we believe, like, it's a very powerful tool. So if you guys, like, have any interesting research idea that, like, that we can help, let us know and we would be more than happy to collaborate. I'm going to put the link in the Zoom chat in case.
I see. So Stanislav Ivanich unmuted microphone. Do you want to ask a question?
No.
Oh,
okay.
Jay.
One like, the other thing that I would like to mention, especially, like, younger generation, I'm gonna say it directly, like, make sure that, like, in your research, do not reinvent the wheel. Okay, like, this is a very common mistake, especially, like, when it comes to programming and coding. Like, many students, like, when they want to do a project, like, they start from the scratch, and by scratch I mean at the very, very, very fundamental level, and they want to build everything themselves. It's very good practice for learning, don't get me wrong. Like, when you want to learn, that should be the approach. But when it comes to, like, delivering, doing research, and, like, and moving on, opening up, like, new frontier in science, you always stand on the shoulder of somebody else who came before you. And that's the story of like, that I'm trying to tell you. Do not reinvent the wheel. Like, there are many interesting functionalities that are available in different, packages, different platforms. Learn them. Okay, like, that's very important, that you guys should like, know like, what has been done on that very specific topic. Like, what exists. Basically, what I'm telling you is what exists. For example, like, as you guys may notice, when it comes to fancy, like, if somebody wants to do quantum machine learning in a very fancy way, our honest response would be maybe Wolfram Mathematica is not the best tool because you're going to have lots of headache. But when you want to do like, algebraic computation, we're going to tell you, look, we have, if not the best, one of the best, platforms out there. So that's the thing, like, especially younger generation, keep that in mind, like, learn what exists out there and use them. You'll be surprised, like, many people, like, important influential researchers, they spend their lifetime like, developing some libraries, some functionalities. Just use them. You don't need to reinvent the wheel and start from the scratch yourself.
Yeah, thank you very much.
Take home message.
Yeah.
Okay, I think it's a good point to wrap up this session. Like, any other questions that you guys may have? Keep that in mind. I'm going to put in a Zoom chat. Our email is quantum@wolfram.com. Feel free to reach out. Don't be shy. Like, look, if you see the silly code questions that I'm asking Nick, like, you'll be surprised. Like, it's just, coding is not easy, even for like, trivial things, you may make, silly mistakes. If something is not working in Mathematica, don't curse at us or Mathematica, just send an email. Hey, I tried these things. You told me it works, but it didn't. That's my job to help you guys. So don't be shy. Even like, simple questions, please ask us. And good luck with everything that you guys are doing. And, stay safe, everyone.
Thank you.
Thanks a lot.
Thank you.
Thank you, guys.
Thank you.
Cheers. Have
Yeah.
a good day.
You too. Thank you very much for such nice talk, and yeah,
Very
we
impressive.
learned a lot.
Likewise. All the best,
Yeah.
everyone.
Goodbye.
Thank you. Goodbye.
All the best.